So we are okay, Bruno. Already broadcasting the presentation.
Okay, Julio, thanks. Okay, so good morning, everyone. We are starting day 3 of the Latin American Robotics Symposium and the Brazilian Robotics Symposium, edition of the year 2020. Right now, I would like to present today's keynote speaker, Professor Luc van Gool. Professor van Gool was born in Leuven, Belgium, where he studied electrical engineering at the University of Leuven and got his PhD degree from the same institution. In 1996, he became a professor in Leuven, where he still leads a research group focused on industrial applications of computer vision. In 1998, Professor van Gool became a full professor at ETH where he is the head of computer vision laboratory at the Department of Electrical Engineering. With his research teams, Professor van Gool is a partner in several national and international projects, ranging from fundamental research to application-driven developments. He's also co-founder and director of the company iTronics, that specializes on 3D modeling and animation for entertainment and medical applications. Professor van Gool has been a member of the program committees of several leading international conferences, such as ICCV, ECCV, and CVPR. In 1998, he received the David Moore Prize at the International Conference on Computer Vision. According to Google Scholar, he has more than 132,000 citations, being part of the selected list of the top 10 computer vision researchers with most citations. We believe that a few people actually know it, but we think that Professor van Gool likes Brazil so much to the point of being a regular visitor of our country. We are, of course, very happy about this and ask if this is the case, hoping that he could confirm this at the end of his talk. Welcome, Professor. Many, many thanks in advance for accepting our invitation. And you can start your presentation. Thank you very much.
Okay, can you hear me? All right.
Yes, we can.
Okay, thank you. Obrigado, Bruno, pelo convite. So I will talk today about autonomous driving, more than what meets the eye, meaning that, of course, cameras are probably the primary source of information that allows for autonomous driving. So cameras installed on cars that are supposed to be autonomous, so self-driving cars. But then I will talk about a few more issues in the second part of the talk that also come in and that have to be covered in order to make autonomous driving a reality. Important to the talk of today are also contributions by the people leading the actual research teams working on autonomous driving in my two research groups. One is at ETH in Zurich, and the other is at the KU Leuven, the University of Leuven in Belgium. And these are Mark Broesmans leading the results and the work in Belgium at KU Leuven, and Dr. Denshin Dai, who's leading the research at ETH Zurich. Okay, so good. So here's an overview of what I will talk about today. First, I will say something about what we do with the cameras. As I said, these are probably the most important input devices installed on the autonomous car. And then I will say a little bit more about additional things that we have to take into account as well to let autonomous cars drive well. And one of them is how to use maps, map information, like also navigation systems would supply to human drivers. Also the possibility to talk to your car and give your car instructions or interact with the car. And then finally, the fact that people, of course, not only see when they are driving, they also listen, and they get maybe not so consciously, but they get a lot of information actually also from what they hear and not only from what they see. All right. In fact, we have done many more things that have to do with vision for robots. This is a robotics audience, so I think it's maybe interesting to give a quick overview of a number of things we have been doing for other things than just autonomous cars. We have been working on intelligent wheelchairs, which need pretty much the same kind of autonomy if we have very deprived patients using them. We have been working on mobile mapping robots for the catacombs, so making a precise three-dimensional mapping of the catacombs in Rome. We have been working on a robot for eye surgery, where the stability of the robot hand is crucial to do the very fine-grained surgery on the arteries that you find in the retina. We have been working on robot for city navigation, so bringing packages and so on, having to automatically negotiate traffic and find a way in cities. We have been working also in space, so with the Japanese space agency and the European space agency, where you have a robot mounted on a satellite that goes out to repair other satellites, rather than having the high cost of building satellites anew and launching them, and several other things. But today I want to focus on autonomous cars. And autonomous cars are a very interesting field of research for us as vision researchers, because so many different aspects of vision are actually needed. So if you want to have a car driving autonomously, it has to take over many different roles that normally human observers would take for granted, right? You have to recognize other objects, other traffic agents. You have to get an idea of distance to other traffic agents. You have to track these agents. You have to get an idea of where the lane markings are. You have to be aware of traffic signs and so on and so forth. And if you want a car to really autonomously drive, it's not enough to just take over part of those things. You have to take over the entire lot. And that means almost like the entire field of computer vision comes in if you want to build an autonomous car. And of course, that makes it interesting for us also because you have to combine all the things at the very same time. Okay, so first I want to give a little bit of an overview of the things we have been doing for the camera input. And then I will go on with the three other parts of the talk as I was talking about before. Yeah, so we are working under this umbrella called TRACE. This is Delta Research on Autonomous Cars in Europe. So we are, in fact, a grouping of multiple research institutions that work together on the generation of autonomous driving. And these groups are in Prague, the technical university there, the University of Cambridge in the UK. We have ETH in Zurich and TRACE-Leuven, of course, the two groups I lead. And then also there's one more group there in Saarbrücken, which is actually the Max Planck Institute. And so these groups together form this entity called TRACE. Yeah, that actually is supposed to be a video. So what I will talk about today is all work together with Toyota. This is our industrial partner. And we are, in fact, the European branch of the research on autonomous driving that they are doing internationally, also in Japan and United States mainly. Okay, so of course we have to work on sensory input, and there are multiple sensors mounted on those cars. Depends from one model to the other what exactly is mounted on them, but we have all-around vision. And I think that is one of the biggest advantages that autonomous driving will also bring, because humans look forward, or they look in the back mirror. They try to get, of course, an awareness of what's happening around them. But here you have sensors, and they're looking all around the car continuously the entire time. And so with also constant attention, they don't dream away, they don't get a phone call, they are not looking at their Facebook pages while driving. Of course, you would never, but nonetheless that happens, and it's the cause of many accidents, unfortunately. So autonomous cars have this constant all-around attention, and I think that will be a major advantage when trying to build safe systems. I also have to say that in the case of Toyota, we are at the European side, at least, we are mainly looking at what we can do for consumer cars. So if you talk about autonomous driving, you have these different markets. You have kind of a market segmentation between one thing that is autonomous driving as a service, the Ubers of this world, the Lyfts and so on. On the other hand, you have the personal car, a consumer car. And the demands on these two worlds are quite different. If you have a car that you just use to go from A to B, it's not your own car, just your next Uber, and you're doing the whole thing autonomously. In fact, that is easier in a way than having a consumer car that is autonomous, and for a number of reasons. First of all, if you have a car as a service, it's on the road almost like constantly. So you can write off costs more easily, because the usage of the car that is used as a service is more intense and throughout the entire day, probably. So that means you can have more expensive equipment on that car and you're still fine. Moreover, you can have also equipment that's maybe not so nice looking, because this is nobody's personal car, so you couldn't care less, right? It's a car that you just use to go from A to B, and that's it. But if you buy a car, you want to have a cool car. It should look nice, and so you should not have a coffee mill, which is a Lidar sensor on top of the roof, sticking out and being pretty ugly, actually. Everything has to be looking nice if you have a personal car. So that's another difference. Last but not least, if you have a car as a service, that car can be confined to a certain region. It can provide its service in only an urban environment, and you never will go outside. So it has to know about one particular environment pretty well. If it's a personal car, you never know where that car will go one day. So you have to be much more wider in the applicability of the autonomous driving. So autonomous driving on a consumer car, it may sound like that must be easier because less professional and so on. No, actually demands are much more stringent than if you would have autonomous driving as a service. I just wanted to give that away. Right. So I will first talk about cameras, but of course, if you talk autonomous cars, there are many more sensors on them. You have Lidar for depth extraction, like you have on so many mobile robots. You have also radar. That's very good because you can see through fog and in different difficult conditions. You have ultrasound for nearby contact dangers. Then you have the inertial sensors, and finally GPS telling you where you are in the world. So you have this entire ensemble of different sensors that need to be integrated actually to make sense of them. But as I said, first we will go for what we do with the cameras because they are closest to what humans do and are probably the best replacement of human sensing in that sense. Okay, so one of the things you want to do is to get this awareness of what is happening around the car, and part of that would be like the segmentation. So on the left you see, in fact, the car driving. You see that with the virtual object here, so that would be the own car. And then you have the world around that, and we have an idea about distances from that car. So it is a textured representation of that environment. In the middle column, this is a video and we'll start playing it soon. You see the segmentation. So here you have purple being road. You would have the lane markings, the road markings being red. Like here, you would have green vegetation, and you would have these poles here, yellow, other cars being brown, and so on. And then on the right-hand side, you see the conclusion from that analysis, where you have green as being free space where you could go next, and red space where you should not go without causing major accidents, at least. All right, so here you see the system at work. So of course it has to work at a high speed. We have to do this information acquisition several frames per second, at least 20 frames per second, if possible more than that. And you see the system evolving as the car moves ahead. So you see the world changing around the car as it goes through this environment. So this is segmentation. It's segmenting the entire scene into the different kind of classes, like cars, vegetation, road, lane marking, poles, and so on and so forth. So about like 20 classes in total that people typically make a distinction between for autonomous driving in benchmarks. All right, as I said, of course, we have vision all around the car. There are forward-looking cameras, but also sideward-looking cameras. And here you see a representation of also the part of the sideway information with segmentation going on as we drive along. In the box on the right bottom, you also see the indication of the different lane markings that are being extracted, and about which I will also tell you more in a second. Right, so segmentation. Now, segmentation usually is not enough. You don't want to know about the regions that cover cars. You want to know about the exact regions in different images that correspond to individual cars. And whereas the previous overall segmentation in 20 classes would be called semantic segmentation, making distinction between the different instances within a class, like different individual cars, that's called instance segmentation. And that's harder to do than semantic segmentation. So we have also been working on this instance segmentation type of analysis. And here you see an example for cars, but you can do that for multiple different classes. For instance, in the next slide, we will have pedestrians, also important, of course. So we want to also distinguish individual pedestrians from each other. Much more complicated objects, actually, pedestrians, because they are so non-rigid, obviously, so much more variation in their appearance, and smaller, which also is not really helping if you want to do that segmentation. Okay. So we have built our own instance segmentation approach, and it's state of the art still. So on the left, you see, in fact, an example of a plant, and just another example that has nothing to do with traffic, obviously. But here in instant segmentation, you don't want to just indicate where leaves are. You want to identify the individual leaves. Now, what neural networks and the entire thing I will be talking about today, it's all based on deep learning, on deep neural networks, and in the case of images, typically convolutional neural networks. So what they are very good at is building this very rich representation, and it's difficult as a human to wrap our heads around what's going on in that representation space. But a lot of the performance of neural networks actually comes from the richness of that space. So what you see here, that is we define a loss function so that, in fact, pixels coming from different leaves are also grouped together. So the different leaves are grouped together. All the pixels coming from one separate leaf get a representation in this feature space, and I can only show 2 dimensions. Of course, it's much higher dimensional in reality, but these pixels are getting a representation, a feature representation that is contracted, that is getting closer together, while the pixels belonging to different leaves are pushed apart. So that loss, that discriminative loss that we have here, is defined in a way that pixels belonging to the same leaves will come closer together in the representation, and pixels belonging to different leaves are pushed further apart. You will see that step after step as the training of this network proceeds. So that the next step, and you see, in fact, these different leaves, and you see the color code on the right of the pixels belonging to different leaves, and then the representation with the same color in the middle. You see that evolve to a pure and pure segmentation of the different leaves in that image. Okay, and that I think is the final one. So where the segmentation is pretty perfect. And you can, of course, train a network for different classes, like you can do for the sticks on the left and also the cars on the right. The cars on the right you saw before. Now, remark that for the sticks on the left, you have sometimes quite complicated occlusions, in the sense that one stick may actually interrupt the image of another stick. But you see that the classification of the individual sticks, this instant segmentation, nonetheless goes well and is in fact correct. So you have the ground truth in the middle column for the 2 scenes on the left, and then you have the instant segmentation coming out of our algorithm on the right. And it's indeed following reality pretty closely. Okay, so instant segmentation, we need that all over the place to identify individual people, pedestrians, cars, but also lanes. By the way, here's more information about how we do this, if you would be interested. Okay, here we apply the same kind of instant segmentation, but now to different lanes. So you see the instance or the object at the top level, and then left upper corner, and then below you see the different lanes being identified. You also see the fits of the splines that we have in the end on the right hand side to do these lanes. By the way, this happens at about 50 frames per second. This is for the TuSimple benchmark. You also see that there are different ways of separating these different lanes. Sometimes there are lines, sometimes only knobs, like here, and still you have to be able, with the same algorithm, to treat all these different cases. So you cannot expect a nice line to be there all the time. Sometimes there hardly is any line at all, even not really knobs. And of course, you see also there are different types of lines, right? Sometimes there are these just full lines, sometimes there are lines you can cross, and you also want to make that distinction. And this information for an autonomous car obviously is very important, because you have to be aware of these line markings and these lanes that you have to keep with your car. And if you want to cross them, you have to make sure that you have the freedom to do so. There's no car coming from behind that would block you the way or make the crossing extremely dangerous. All right. So here you have on the right-hand side the distinction made between a full line and then a line that you can cross. That's one distinction we have to make if you want to drive safely with this autonomous car. And by the way, a big challenge is that, of course, roads are not always nicely planar. So a pure planarity assumption of the road ahead is not a safe assumption to make. You have to be more flexible than that. Okay, and on the left-hand side, we have another video here showing, in fact, the lane on which you are, which is the blob, and then you have these squares. These are the other lanes. With green lines, we indicate lines that you can cross. Red lines are, again, lines you must not cross relative to the ego lane in which you are. Okay. So, of course, there are many things we have to take over from human vision if you want to drive autonomously, as we already indicated. So one thing would be to also automatically recognize all the different traffic signs that may happen on the road. And these traffic signs are not the same from country to country. So there's also this issue of automatically retraining to a new country or making that very easy to retrain. It's also quite appalling in what state some of these traffic signs actually are. One must not underestimate the problem of being occluded by trees, being bended, people putting stickers on them, and so on and so forth. So there are serious degradations to also take into account. And we also built special networks to deal with those issues. So here you see the traffic signs being identified together with an identifier of what traffic sign we are looking at. So that, of course, we know what the consequences would be in terms of maybe a speed limit or a one-way road or something else. So, yeah, having to give preference to all the drivers and so on and so forth. Okay, so another thing we had to implement, many people did in the meantime. This is another example of something that we want to do, especially for motorbikes, because they are dangerous. So these are the manholes. You see one indicated here. And if it's rainy, they become quite slippery. So for motorbikes, it's important to be aware of them before you slip and fall. So we have also built some software to detect them automatically and so that people can be aware of their presence. Okay, and you see again around this middle image, different images taken from that car all around to the front, to the back, and so on. And we do the analysis in all the images combined. Then I mentioned there are so many things you have to take care of. Well, tracking is one of them. So here you see, in fact, two forward cameras, a bit the wider angle camera on the left, and then a more zoomed in camera on the right. And here we have 3D bounding boxes around the objects being tracked around the car. And the same thing has to happen also on the sideway cameras and camera looking to the back. And of course, you have to also re-identify the cars. You have to be aware that the car that you first see maybe from the back is now the same car that you see on the side, and then the car that you see in front. So this re-identification is also an important topic of investigation. Okay, that's the tracking part. By the way, bumps in the road make tracking harder because that also means that the images will become quite shaky. And that's why we also analyze the optical flow. You see optical flow being analyzed here in real time. And that makes that if you correct for optical flow for the ego motion of the car, you can get much more stable tracking than if you don't do that. Well, the difficulties are maybe a bit hard to see, but if you look in detail, like now, the camera will start to shake a bit. The blue thing is more stable around the car than the green one on the left. And that's because we have this ego motion based on the optical flow of the surrounds that we take into account. All right. Okay, here you see the same thing, but now a bit with cameras all around, from the back, the side, the front. And of course, all that information has to be integrated. You see here in this panel, the car, that's the own car. It's moving to the left. You see all these other cars moving around in relative positions, well analyzed as positions relative to the car in different lanes. Good. Another thing I've been talking about is trying to get at the 3D layout. Now, more and more we try to do that without Lidar. And the reason is that if you have a high resolution Lidar, so a time of flight depth sensor, it's quite expensive. So if you have a Lidar with like 64 lines, like the Velodyne with 64 lines, that may cost you quite a penny. Okay, we are talking thousands of dollars, tens of thousands of dollars actually. Whereas if you have a car, typically car manufacturers are very wary of spending too much money on any component because the margins are rather slim. So the cost on any component on the car has to be cut down as much as possible. So no way you will put $1,000 Lidar on any car that will hit the road. Right? That may be nice for research. It's just not viable for a commercial car. Certainly not if it's a consumer car. As I said before, if you have driving as a service, maybe you can spend a little bit more, but if you have a consumer car, better not. You don't want to go there. So one of the things we have also been trying to do is to look at cheaper Lidars. And that would be Lidars that have fewer rows. So the original Velodynes, these coffee mills that turn around, had 64 lines, but you have now these pucks, these cheaper Lidars, and they have fewer lines. So resolution is also going down with cost. So 16 lines is quite a few less than the 64. That's what I had before. So the question is, can we still use those low resolution Lidars in combination with RGB cameras to get a high resolution depth image? So you have the high resolution coming from the camera, and the camera is rather cheap. Then you also use a cheaper Lidar with only a few lines, but that gives you a little bit of ground truth, kind of, for distance at the 16 lines it has, or even fewer. And the question is, can't we then boost the resolution back to the resolution of like 64 lines or close to what the RGB camera actually would offer? And here you will see a result. I have to say that, of course, when it depends on car manufacturers, they would even like to go further and only use cameras and get a depth estimation just from a camera, even from a single camera. I'm not even talking about stereo cameras here, but just monocular depth estimation from a single camera. And we are also working on that. I think you will see an example of that later as well. I'm not sure. Anyway, so here you see now the 3D reconstruction of a scene. It's looked at from a different position than the sensors, so it looks a bit awkward if you look from the top, because there are no depth data there. But you see, the distances extracted here make sense, and it's much more dense than just 16 lines by combining indeed this camera and low resolution Lidar, sticking at low cost, but having much higher resolution depth than before if you would just have the 16 line Lidar on its own. All right, so here you see some results. So the top is the scene here, and then these are different methods. The bottom one is our method, not the most recent, but one of the older methods. And you see that actually this method on the bottom is more precise. It has better delineations of this car, for instance. And if you look here in older systems, that is a bit more noisy. This is better delineated. Also, the poles and fine structures are better delineated than the old systems would. So, yeah, that's an example of sensor fusion, as I said. So, RGB camera together with low-res Lidar. Okay, and then, of course, we have to bring everything together into a single system. For that, we are also using multitasking. I will say a little bit more about that later. So here you see how the input from the different cameras mainly is being combined. So you have the different aspects here, the segmentation, the free space analysis, the lane markings. Yeah, here also the individual lane markings actually being separated, and so on and so forth. And also here's instant segmentation of the different cars. More of the same. So yeah, everything has to be integrated into a single system, obviously, from which you can then draw your conclusions how to drive. Or here you see also some of the sideways cameras pretty well. These are cameras from the side. Here you see also tracking bounding boxes indicated down below. Not very visible, I can imagine, but nonetheless, yeah. Okay, so that is in fact the entire story, mainly based on cameras. But of course, you can then boost the results further by having additional sensors. Yeah. We also indicate dangerous situations, like in this case, like a pedestrian coming in front of the car, which is indicated in red, as you will see. As a pedestrian to, yeah, be careful about not hitting. Okay, so then I mentioned multitasking before. So multitasking means that you are trying to solve multiple tasks with a single neural network. So traditionally, you would have like one task like stereo or tracking or segmentation. Now, of course, as I said before, in an autonomous car, you have all those to do all the things at the same time. So we have built these multitasking networks that try to combine in a single network multiple tasks. Now, there are reasons to do that multitasking kind of approach. And so I have these reasons here on the right. So one of the things that you are going for is that hopefully by sharing part of the feature extraction between different tasks, you don't have to re-extract the same kind of features over and over again. So that will then lead to an overall network that is leaner than if you would just combine individual networks for different tasks. Secondly, because you don't have to recalculate the same features over and over again, you can expect the overall computation to also go faster. And finally, and this is more philosophical in a way, you would hope that by having a network that is exposed to multiple aspects of the world, like the world having depth and being dynamic and consisting of multiple objects, as in segmentation, that in fact all the other tasks benefit from each other's presence by being trained simultaneously. So that the network, this multitasking network that's doing multiple tasks at the same time, gets better at all these individual tasks than an individual network per task would be. Now, that seems to be the hardest nut to crack, because in reality, that doesn't come so automatically. You have to work a little bit on how you do this multitasking to make that last advantage happen. But it does happen in practice. So that's the good news here. You can build this overall network. That's all different sub-aspects of the task of the autonomous driving that you have. It's leaner, it's faster, and it's better all at once. So that's a nice thing. And here we have an example of a task where you have a shared encoder that extracts a common representation of features from the input, and then has different decoders here to do different tasks like semantic segmentation and instant segmentation for cars in this case, and also monocular depth analysis, so trying to estimate depth from a single image. And you have all these tasks happening together, okay? And the network also being trained to solve these different tasks together, building, it seems, a very effective representation to analyze the world. So joint feature extraction, and these features are then used to build different tasks upon. Now, of course, this is a very simple kind of architecture, and optimizing these architecture, you can write an entire book about that single topic, but this gives you an idea about multitasking. Of course, the branching here of these decoders doesn't have to happen at exactly the same place in the network architecture and so on, but okay, gives you a taste. Here you see a video of this happening. It's in fact happening in real time, as you will see. So we have these different tasks that I talked about before. The speed is 21 frames per second. So the video is coming in at the top, and you have these 3 different tasks being done in real time, as you see below. And of course, the monocular depth is not so great as you would have from real depth data, but it's still kind of okay. So it's interesting that you can still get reasonable depth estimates from a single image, which of course, purely mathematically, in a geometrically correct way, is not possible. It's knowledge about the world that brings you that information. By the way, it's trained from having Lidar data or stereo data available during the training as ground truth. Okay, so another important topic on which you are working quite extensively is also dealing with difficult circumstances like nighttime. You still want to do a segmentation, and of course it will suffer, but we try to get it at a good quality at least. And so this is a matter of style transfer. Here's another example. We have different levels of fog. So we start from a fogless environment, and then we add artificial fog to train the system so that it can do the segmentation still quite well under more and more foggy situations. And of course, you have the same for rain and snow and so on, because that's an additional complication that you have with autonomous driving. It has to work under all circumstances, not only the nicest. So again, here you have a fogless environment. We add artificial fog from estimations of depth, and that gives you these foggy images on the right of that. So the nice thing is here we have better conditions to do good segmentation, also manually done in this case. And then that is good information to train on for these foggy circumstances, because the content of these images is identical, because these images are just generated artificially from fogless images. And that allows for the training of detection under foggy circumstances. Yeah, I mentioned the wheelchair. Here you see an example of such a wheelchair maneuvering in a world that is full of pedestrians. And so again, the same kind of task I've been talking about before is going on. You look at people where they are with respect to your own mobile platform. You look at the ego motion from the static part of the scene. You track everything around you to get indeed an interpretation of trajectories respective to your own platform, and then decide on where to go. On the right-hand side, you see these green areas. They are the areas where you can freely go, and the other areas are areas you have to steer away from because they're occupied. All right. Yeah. then I briefly want to say something more about the cameras, because if you look at nature, of course, there are so many kinds of eyes. We don't only have the typical RGB cameras. Nature has many other types of eyes, and I think there will be also a big space for research in the future, optimizing the sensors for specific tasks. Like a task could be autonomous driving. And it's absolutely not clear that an RGB camera is the best camera to use. Probably you want a camera with different resolution, with different spectral bands, maybe different speeds, and so on and so forth. Okay, so I think, yeah, big area there. So here you see just a couple of eyes in nature, all so very different. Like this is the goat. It's interesting, it has this slit here to have good horizontal vision. So yeah. Anyway, short remark here. And now let me go on to the second part, and I have to go a bit faster through that, I think. First is using maps. So humans, of course, are very well aware of their environment. They are not only using the cameras, they're also often using knowledge about the environment. Often they drive close to their home, or they're going from work to home. They know that environment. They have a lot of information. And if they don't, they still have the navigation system to look at. And the question is, okay, how can we start building in that kind of additional contextual information into autonomous driving to make it more stable and of higher quality? And what we are actually going for here is an end-to-end driving model. And that's different from the compositional model I've been talking about until now. So until now, I've been talking about tracking and object detection and what have you. So here we take a different and a bit complementary point of view, where you just have the visual input, and from that you decide on two things: the orientation of the steering wheel and how far to push the speeding pedal. So you have these two things. You set your steering angle and your speed. These are the two outputs of this network based on the input. So you go directly from the video input to these two outputs, per frame, steering angle plus speed. And we want to make that entire exercise of driving, we want to make it not only accurate, staying close to what humans were doing in that circumstance because we measure it, but also to make it comfortable and to make it human-like. So you would not want to sit in a jerky car where you have high accelerations and then decelerations all the time, and you start to feel ill after a while. Right? You want to have a comfortable ride. And that means the second derivatives of the angle of the steering wheel and the speeding pedal, how far it's put in speed, should not be too big. And thirdly, you want to have a human-like driving. And the main consideration is here, that is what humans would expect, at least for now. And it will also be interesting in the beginning of autonomous cars that you have this mix of human drivers and autonomous cars all together sharing the road. And then human drivers will expect the autonomous cars to behave pretty much the way humans would do. So you want to have this predictability for humans so that you can avoid accidents. So we have these three things: accurate, staying close to what humans do in terms of steering wheel and the speed pedal, but that's not enough. You want to have the comfortable experience, no jerkiness in the driving, and the overall behavior to be human-like, whatever that means. And of course, the neural network is very good at picking up these subtle signals of what is human-like, because a human would find that very difficult to define, actually. Okay, so in terms of accurate, as I said, similar steering angle and speed as a human driver has at the same moment in time, the same environment. Comfortable meaning driving models which short prediction span, they yield jerkiness, and that's bad for human comfort, so you want to reduce that. The whole driving has to be human-like. That's important when you have a mix of autonomous and human-driven cars. And the criteria are here indeed a kind of L2 distance in terms of steering angle and speed, so that's simple. Second derivatives in terms of jerk, these two characterizations, angles and speed. These second derivatives should be small to have comfort. And finally, most complicated human-like behavior. So what we actually trained was an adversarial network, so GAN type of network, that tries to distinguish the driving style of the autonomous car versus human driving. And we try to push, of course, the autonomous driving towards a position where that discriminator can no longer tell the difference, whether it's a human behind the steering wheel or you have this autonomous car. So we collected a big data set, 60 hours of driving in total. We have surround cameras. This is about 3,000 kilometers, by the way. We have GPS also to train this system. And we also add some map information. And in our case, that comes from Here Maps. So here's a company doing these maps, and they have information about distance to an intersection, distance to the next traffic light, distance to a pedestrian crossing, distance to a yield sign, and so on and so forth. So we start to add all that information into the system. And then if you look at the different criteria that we had, so it's interesting here, this is a kind of an ablation study with only a camera up to where we have camera and map data, and also add optimization for comfort and optimization for human-like driving. Also here, if you have the whole lot, you see that in fact everything goes better, and that's interesting. So if we only look from the camera images and try to predict the best steering wheel angle and the best speed, or we add all the map information, like here, I won't go to the in-between case we don't have time, I think. You see that, in fact, even the steering wheel angle is closer to what humans do, just based on the additional map information. And also this speed is better than before, only having cameras, by adding map information. So that's very good. And of course, also the comfort. This is the latitudinal jerkiness, and the longitudinal jerkiness should be down. These arrows mean best numbers are low, okay? So we go down here as well, compared to the original values, based on camera information only. And H means human-like, should go up. You want to have it more human-like, a higher value. And indeed, that also climbs up as we add the map information. And of course, especially if we also optimize for human-like driving. So the end of this exercise was that by adding map information and explicitly going after comfortable driving and human-like driving, that indeed you get much closer to that kind of goal. And here we have an example of that. And at the beginning, we see, in fact, this steering wheel angle, how we indicate it. You see on the left steering wheel angle, right? What the human driver does, what the full model does that we have with maps and everything, and what the baseline camera only model does. And here on the right, you have, in fact, the pedal for the speed. Let me now go to the examples where we have rather good distinction between those. Okay, here we go. So these are a number of examples where you see that only camera, the orange model, is farther away from what the human does than if you have the full model compared to human driving. And that's the blue. These are the blue indications. So red tends to be closer to blue than orange is to blue. And that was the whole idea, getting close to what the human does. So these are all different parts of our data set. On the right-hand side, you see also part of this map information that comes in. Okay. So, let me skip that. More information on this you find here in this paper. So I always gave the archive paper so that it's easy for you to find. Next thing, talking to the car. So the model often is that, okay, you give your goal, you start from a certain point, you give your goal, and then the car just goes there. Now, that's not quite a satisfactory condition because you don't want to be hijacked by a car. It's not like you indicate where you want to go, and once the car starts driving, there is no way stopping it. And you have to go now to your end location, whatever you do. So, of course, while driving, you would still want to take an influence. You would still want to maybe take a pause, have a coffee. You want to maybe take a different route and indicate that to the car. So you want to be able to talk to your car. You want to maybe also say you want to drive slower, or you want to drive to pull the attention of the car onto a specific aspect of the road. Maybe you want to tell it where to park so that it's in the shade under a tree rather in the blazing sun. So talking to the car will become a very important thing. And especially as autonomous cars become more usual, because in that case, more and more people will not know how to drive themselves. So the most natural interaction with the car will be just talking to the car. So here you see an example of this. So for instance, here she says, park to the parking lot next to the red car. For some reason, she wants to be there. And then the car will have to go there. So we have speech. Of course, you have the vision. So this is in fact the speech grounded in visual input. You're talking about a certain aspect that you and the car both see, but the car has to understand what you're talking about in that scene. So the car has a vision, the car hears, and now has to associate the speech, the words in your sentence to specific locations in the image, specific objects in the image. What we, by the way, also use here is gaze. So to disambiguate a bit further, because probably you're looking at the object that you're talking about, if you talk about an object, if that is the goal. Okay, and that would then, of course, be the result of parking. So we have a person saying something, talking about a scene that the person in the car sees, the passenger, and that also the car sees. And then you have also the gaze information. So what is a person looking at? That can be a good indication what the person is talking about, what she's pointing at here. And then there is the scene of the cameras that has to be understood to make the connection with the speech. And we'll have to run quickly through that. So we have the three things. You have the language input here, the speech, you have the vision, and you have the person watching a certain part of the scene. So the gaze has to be analyzed. By the way, the gaze detection, we did not implement ourselves. There we used off-the-shelf tools. Now, of course, a car is a very noisy environment, so it would be naive to hope that the transcription into a kind of a text, the understanding of the words would be flawless. It will actually be very noisy, especially when you're sitting in a driving car. That is probably a particularly noisy environment with much going on around the car. So you have to clean the speech based on what you see. So you have to use the vision also a little bit to disambiguate the speech. So you have to let the visual context influence interpretation of what is being said. So here you see this overall system here. So we have a scene comes in, you say something, for instance, the big window in the middle, and then you have to make sense of that. Now, this scene being, in fact, a scene with windows makes the probability of the sentence being about a window pretty high. And once you have then cleaned the speech, you can try to find what is the particular window this is about. Because in that scene, you have multiple windows. Of course, probably it's that one that you talk about. And that's then the reverse. You now use the speech to, in fact, clean up the indications in the image, having not all these green windows, but only the particular one that the speech is about. Okay. All right, so we have worked on that kind of environment where one is the transcription of speech to be compatible with visual context, and then point two is in fact generate object proposals with the transcribed text now as context. So we use an API coming from Google. If you would say something like the big window in the middle, that may be not the highest probable output. So if you follow the API of Google, the most probable interpretation of that sentence, the big window in the middle, would actually be, in this case, where it was spoken by a real person, the big widow in the middle, which is not quite what was actually being said. The big window in the middle is only the second option, and there are multiple more here. The third one is the big wind in the middle, and the big widow with the middle, or the big wind in the middle. So all sounding kind of similar, and the API not quite knowing which it may be. But of course, then we have also the image. So this would be the image in this case. We have a network that has been trained to now rank order them by probability given the image, so conditioned on the visual input. And that brings the big window in the middle on top and pushes the big widow in the middle down. I've nothing against big widows, and I don't want to separate them from their medals, but nonetheless, we don't want that as interpretation when given the scene on the right. So indeed, that network would, in fact, this network here would, based on the image, disambiguate further and push up the big window in the middle, given the scene. And so we built this network for street scenes. We had to build quite a bit of training material, of course, for that, as always, with deep learning. So we also did that here. So given this general scene, if you then say the woman crossing the road from the left side, it would then identify this as the most probable person belonging to that description. Okay. Yeah, and here we have a few examples where this kind of thing is being done. By the way, what we do with the video data is not only taking the raw video, we also look at the molecular depth estimation, and we also extract the optical flow. So we have all that type of information. So this would be one of these training scenes. The speech will be about the car. So this is a gaze analysis, right? So we try to see where the person is looking at. Probably that's the object he's referring to. So we have appearance, depth, motion, language, and speaker's gaze. So this would be the molecular depth estimation. So the brighter green is closer, more red is far apart. This is the optical flow analysis, kind of the overall motion that you can find. Of course,
a white car parked behind a gray car on the left side of the road.
So here it describes, we look at where it's looking at, and then that would identify the person. Okay. The different inputs all coming together and then identifying the object that we think is talking about. The car, these are all the cars, but that's the case also indicated. And so the most probable is this white car in the green box. So, and that has been done on a very extensive data set, always using the same kinds of input.
A gray car in front of us, moving fast on right side of the road.
So same story here. That's probably the object being talked about. Okay, and so on and so forth. So here you see different examples. It not always goes well. So we have first two examples on the left where we have a correct analysis. So the top row would be the video. There you also see the person with speech and engaging at the scene. The gaze you see here in the middle with the red spots with the halo around it. So the objects that the sentence seems to be about are highlighted here, like people or cars and so on. And then finally in the bottom row, you see the predicted box in red, and then the actual box around the object that's really meant in green. You see the two columns on the left. There we have a correct prediction, so the red and the green box are coinciding if you look at the lowest row. But then on the right hand side, you see mistakes being made. So sometimes quite bad mistakes, like here on the right-hand side. So still more work to be done. Okay. Here's a paper, or two papers actually, about this particular subject. Again, you can probably look that up in YouTube video afterwards. Then last but not least, of course, people while driving, they listen into the environment the entire time they are driving. And there is sometimes important information coming from nothing but audition. So if you have, for instance, a siren of an ambulance coming from somewhere, you hear it probably before you see it, right? So it's important to be aware of those things. Also, weather conditions, often you can hear that from the sounds that you have a wet road surface. You can often estimate things like that, how much grip your car will actually have based on the sound. This is not what I will talk about here. I will talk about the objects that seem to be making sound around you, and that also builds part of the awareness that human drivers have of their environment. So they don't only see all the objects around them, they also hear them. And that's an important part of that all-round awareness. And so we want to also emulate that, we want to mimic that oral awareness. So human drivers not only watch but also listen, and our goal is here to localize certain sound-making objects of different types in noisy environments, only from hearing in this case. So we want to listen to the world with like two ears, and then tell where the different sound-making objects around you are. For that, we have built a data set on Zurich public streets. You see the map of Zurich there, bottom left, and there at certain crossings, we have taken about 5 to 7 minutes of video with also oral input. And you see the oral input here. By the way, this is the omnidirectional camera. It's a GoPro fusion system. That will take the video. And then below, you have this system with different microphones. And this system has been built to mimic the human auditory system. That's actually all these ears. You see these things really, these microphones here, they have this kind of oral ear shape, right? So here you see a top view of that. And you have in total 4 pairs of microphones put in these positions where normally ears would be. And so we will use the forward-looking, forward-oriented ear pair, and then try to get that map of sound-making objects solely from that input. But okay, so we have, in fact, also microphone input from other directions that we, in the end, will not use for the network, but we will use it for training the network that we'll talk about. By the way, taking these 5 to 7 minute videos at the 165 street junctions, we have, in fact, chopped that up in 64,250 fragments of about 2 seconds in our data set. And for that, we have synchronized video and synchronized audio. So we have both. So that's the task. We have this auditory system. We have the 2 ears, like now not looking, but hearing forward, you could say. And then you all around is a panoramic view of the surroundings. We try to predict where the different sounding objects are. And for sounding objects, we have actually only looked at 3 classes, being cars, motorcycles, and trams. Yeah, here it says train, but it should actually read tram. Okay, now in that process, again, in the style of multitasking and trying to beef up the performance of this prediction of where the sounding objects are, we built 2 auxiliary maps. One is a super resolution map for the auditory input, and one is a depth map. And in the end, all three maps will be built from hearing only, and will be built up all three with a multitasking network. But as a result, this segmentation map will improve. Okay, it's multitasking philosophy. The philosophy here has been that we train this auditory system, because now we have input only have audition, we only have the two microphones representing these two forward hearing ears. And we train that from vision, because vision is probably more precise. We don't want to do hand annotations, but we feed the system with what the vision system thinks is correct. And then we try to get as close as possible to what the vision would do, but now with the ears. And the question is how good we can do that. Okay. So these are the two auxiliary maps. On the left-hand side, you have this auditory super resolution map that we tried to build. So we have, as input, only have this. But that is what we tried to get. And in fact, also with 45 degrees in between. So we have these 8 different orientations. It's like you have what you hear looking forward, and then you mimic what would happen if you would turn your head like 45 degrees and then 90 degrees and so on. 8 orientations in total. So you're trying to predict that. Now, of course, we have these additional pairs of microphones every 90 degrees. So for some of these orientations, not for the 45 degrees one, but for 90 and 180 and 270 degrees, we have ground truth because we have the microphones. And that we will also, of course, use to train this or super resolution system. And by the way, this is the depth map that we try to get from the audition, from just listening. Okay. Okay. So, all right. Yeah. So multitasking approach, as I mentioned. So we will steer the whole thing. We will train the whole thing through vision, and then end up with the system only steered by ear input, by microphone input. We teach the audio students, in fact, from these visual teachers. So we have a kind of student-teacher thing here, where the teacher is the vision and the student is the audio. And of course, for the actual evaluation, what we used was manual annotation to be really certain that we were not hallucinating solutions. So as I already said, we have a focus here on cars, trams, motorcycles. We are not dealing with pedestrians here. Pedestrians, of course, are more difficult to segment even. We are also not looking at buses and all the things that at some point we have to include, by the way. So we are looking at the central frame for each of the 2-second segments that we have acquired. So that's where we do the analysis for. That's also where we, in fact, validate for. So on the left, this is the visual input. So we have these 2-second small video fragments. So what we do is we look for the 3 types of objects: cars, motorcycles, and trams. And then we look for those that move. And we do that with background subtraction. And that gives us, in fact, the moving car, the moving motorcycles, the moving trams. We say, okay, these are the sound moving objects. Now, then also the vision will do the segmentation that you saw in the first part of the talk. And you see that actually here on the right-hand side. So this is visual input. And that's used to train this audio system. And then we have these 2 additional auxiliary maps I mentioned. The super resolution oral map, where we use the 3 other pairs of microphones as ground truth, and also the depth map, where we use monocular depth estimation, again, not our own, but mono depth to an existing network to do that. And again, to train this oral system. So the overall network, as said, implement as a multitasking network. It has, again, very simple architecture, not necessarily the best one. It has one shared encoder and then separate decoders for the 3 tasks. And that way each task is allowed to benefit from the others as we would hope for, and therefore results are boosted compared to what we would get if we would train individual tasks or networks for individual tasks. Here's the overall structure. So on the top, you see that the vision is used here to do this segmentation of oral objects. It gets an input from the vision pipeline here during training. And the network tries to mimic that with its sounding object segmentation. This is in fact a map that is being trained here. Now, the same for oral, super resolution. So we get only a pair of input signals here on the left for the forward ears, let's say. And then here is generated the noise that is coming for other directions. If you would, like simulating, if you would turn your head around, what you would hear then. And on the bottom, you have this depth estimation, again, using the vision as an additional training input. But that's all training. And this is what happens in inference mode. So later we use only the input from the forward pairs of ears to generate the three types of output, the three types of map, sounding object map, prediction of what will be here if you turn your head, and also the depth prediction around you. Again, this is all panoramic, okay? So it's going completely around. Here's some results. So on the left, the scene that you see, and then here on the left, you have these segmentations for the sound making objects. Not always correct. You see here, this is a little bit of nonsense that you find, but nonetheless, on the whole, it makes sense. It's not completely off, let's say. It really makes sense what you have here. Like you have here this tram, and you have that also from the vision input. You have a car here. It's coming pretty close to what reality should be. This is a depth prediction from sound alone. This is ground truth. Well, ground truth, this is what you would get from the vision, which will be closer to the truth, of course, but it's not really ground truth. But you see, there is some similarity here at least. You have a little bit of an idea that something is closer here, for instance, as it is also in reality. And on the right-hand side, the top would be like the forward hearing signal, and that's one of the predicted signals for another orientation, and that will be the ground truth. And you see there are quite good similarities here with the peaks coinciding pretty nicely as it should, peaks that are not in the original signal at all, as a matter of fact. So all in all, that learning goes pretty well, I dare to claim. One more example. So on the left, you have, again, these middle frames of these 2-second fragments. Then you have the noise making predictions here on the middle. That's, of course, the main output of the system. And this is from vision. And again, reasonable consistency between what the vision would do and what now you do only based on hearing. And this is a paper where you find more information on this part. And that concludes my talk. Thank you very much.
Thank you very much, Professor Van Gool, for your impressive talk today. I'm sure we have questions from the audience. We were taking questions from the audience. We have time for that. I think there are questions from YouTube. Professor Fernando Osorio is asking, I think humans in autonomous vehicles based on vision cameras have both almost the same limitations in adverse conditions. I hope in the future, autonomous cars should be safer and use better sensors. It is true that the price is very high for some sensors, for example, Lidars, but I think the safety should be always in first place. So we need to develop cheaper sensor devices. In Brazil, one big problem are also the motorcycles and motorcyclists. It is hard to think that we have autonomous motorcycles in a few years. So here we have an important problem to deal with. Not exactly a question, but I could, if I could make this a question, I would ask, how do you see these systems, or what do you think would have to be adapted to tackle some very specific traffic problems, region by region traffic problems? What do you think about it? For example, here in Natal, the traffic is, has some characteristics that I'm pretty sure in Zurich are different, in Leuven are different, so on. City by city characteristics of traffic. What do you think it would be necessary for autonomous systems to deal with these conditions?
Yeah, I think there are multiple questions here. First of all, about the different sensors, I fully agree that we have not reached a point where we are really optimizing sensors for autonomous cars. So for instance, Lidar manufacturers are working hard to reduce costs and so on. For the moment, still pretty much at the expense of resolution, which of course is not great because, yeah, there's only so much you can do then in reducing the price. But technologies are improving, and this also touches on the point that I made before. Probably we have to learn to optimize our sensors for driving. It's not necessarily the case that, for instance, the best camera is the normal RGB camera, which is a little bit there to mimic human vision. But we don't have to mimic human vision in general. We have to get the best sensor for driving. And people don't necessarily have that kind of sensor because driving is only part of their life. They do so many other things with their eyes as well. So you would certainly like to further optimize sensors, but there's one thing, and that's about the adverse conditions that were also mentioned in the question. Yeah, we will have to do something about adverse conditions, and humans are definitely not great in looking into the fog and so on with their eyes, because their eyes have all the limitations, absolutely good point, that also the cameras will have. But of course, radar is far superior when it comes to foggy conditions. And one of the great things, and we are working on that, by the way, but I could not show you results today, on, for instance, combining vision and radar. That's a very nice combination because it's two low-cost sensors. And radar is more complementary to vision than actually Lidar is in many ways. So radar is, of course, a kind of super sense in a way, right? So it can do things that we cannot do with the human eye. And if you then throw into the mix these deep networks that extract these magical features that you would never think about when you have to do it manually, you come up probably with, I would think, adaptive features that change depending on the conditions. So conditioned on the situation outside the car, which you would have to recognize with your input, then you could have a gradual change of selected features to do the job. So like at night, you would probably like to use a different combination of features from radar and vision than during the day. Or if the weather changes, you would probably also want to have these features to shift. And these networks can do these combined sensor-fused features that we can only begin to dream of now. But first results already indicated that these networks can do indeed fantastic things, combining different sensors in ways that we cannot really manually master anymore. And the biggest thing I think is, and we are also working on that, by the way, is you can say, oh, I can do this for that kind of level of fog. We can have this optimized network. And for rain, we have this network. But you would, of course, to have to automatically adapt to the situations around the car. So I think we will have a situation where you automatically have to read the situation around the car and adapt your software on the go based on all the sensors that you have on that car, which is more than what humans have, and will be more dedicated to driving. So I'm quite hopeful that we can actually master difficult circumstances better than people can in the end. Then the other question that you had was also, yeah, the circumstances are different from place to place. Very true. And this is also a little bit like the conditioning, depending on where you are, and the car will tell you, it has GPS, you know where you are, you can start to adapt. So probably we don't only want to adapt depending on the particular city, but we will also want to depend on things like, is it a highway versus an urban scene? You want to probably do things a little bit differently based on those. that kind of additional information. So yeah, I hope that answers the question halfway.
Thank you, Professor Van Gaal. We have another comment from Hélio Azevedo, Professor Hélio Azevedo. He's saying, an essential feature for drivers is danger signs, strange motors, noises, smoking other cars, objects thrown from other vehicles, fire on the side of the road. Your research involves this type of situation, or you know researchers who are interested in these aspects? It's an active question.
So I guess this is about an anomaly detection, basically.
Yes, detecting fire on the side of the road, as Professor Azevedo said, detecting smoke from other cars, detecting maybe following motorcyclists on the road, or a crash ahead of you, something like this.
Yeah. So that's a very good point, of course, very much to the point. You want to quickly detect anything abnormal around you, because probably that has to draw additional attention. Yeah, we have been making some inroads into that, but I would not say we have completely reached the solution there. So there are ways in which you can try to predict the upcoming frames, and if there's a distinction between what you see in those upcoming frames and what is actually what you predict and what you see, that could already be an indication of abnormal dynamics, at least. Smoking cars and so on. No, we have not worked on that yet, but I agree. This is probably what would immediately draw your attention as a human driver. The higher the flames, the more the attention goes there, but we have not been working on that.
Okay, thank you, Professor Van Gaal. Another question from YouTube. Alex Pitt, do you think explainability of models will be an important factor for improving performance, or to satisfy public concerns about safety?
Can you repeat, please, because the sound went away.
Okay, sorry. Do you think explainability of models will be an important factor for improving performance, or to satisfy public concerns about safety?
Yeah, I guess so. And so explainability will be an important issue of all those models, because you want to be able to predict what your car will do, and probably also in the future testing of autonomous cars, because that's another interesting related question. So how do you test these cars? Right? So you have to be reasonably sure that no bad things will happen if you let them loose onto the streets. So you want to test them first under all kinds of conditions. So you want to have some reasonable predictions of what they would really do. So explainability will be an important issue. We all know that deep learning has an issue with explainability, and also with weird reactions like a cat becoming a dog because you added a little bit of noise to the cat image, or vice versa. I think that one of the important things will also be to have some redundancy here for safety, because it's an important word, especially also for Toyota. Toyota don't try to be the first. They would like to be the safest. So there's no push to really be there before anybody else, right? That is not the idea. But redundancy will be important. So I talked about the compositional approach to things, where you have all these different aspects like object detection and tracking and depth and so on, all nicely put together into a system. And then you have this end-to-end learning that could, for instance, be two of these parallel systems. If they are in agreement, that's very nice. If they are not, I'm not sure what to do, but at least we should be very careful.
Okay, thanks. Any more questions from the audience? From Zoom or from YouTube? We don't have anyone. We have 4 minutes more.
Hello, Luke.
Hi.
Let me make one final question, since we are almost on time for starting the next session. First of all, I would like to thank you so much for being here. And I would like to ask you, I think I did this question for you some time ago, but I would like to listen your answer again. how do you see, what is your point of view about it coming from this mathematical approach that are pretty substantiated by equations and complex systems and so on, to this modern data-driven approach. I know and everyone is coming to data-driven approach right now. And how does this affect the way the cars can see or avoid things? I mean, some situation it is necessary to have a very fast answer that a data-driven approach may not give this fast answer to us. Do you get it?
Yeah, so it has been a painful process for us engineers because the whole step towards deep learning is probably a step of making engineers obsolete. Throughout the engineer is a kind of philosophy here. So rather than having trying to be so clever and sitting down and thinking hard about features to extract, now the system comes up and adds 10% to the performance. If you don't have a clue what it's doing. Yeah, and we will certainly see more of that because one of the next steps, of course, is also improving the architecture, by the way. So now we take the architecture a bit for granted. An engineer sits down, comes up with an architecture of a deep network, and that seems to be doing something reasonably okay. So let's train it. And then many people use that kind of architecture for different things, a little bit changing it left and right. But of course, the big issue will be how can we optimize the architecture even by automated processes and throw the engineer out of that process as well. I'm not so pessimistic about fast reactions. I think deep networks will be great in being very fast in reaction they can take. Yeah, equations we all miss, but there you go.
Okay, thank you, Bruno.
Thank you, Professor Luis Marcos, for your question. I think we have time for another question, or 1 minute for another question.
Yes,
No?
sure, go ahead.
I don't. The audience is a little bit shy today, so I'm gonna make my final question. Professor Van Gool, what do you think about the cars being their own like regulatory agents of the law? I mean, in a non-fully autonomous scenarios, do you think the cars could be used to maybe in a vehicle-to-vehicle communication scenario with all this infrastructure ready, as Professor Fernando Sawyer said on the chat? Do you think cars could be used to apply penalties to drivers? I mean, the car has detected that the driver is drunk, maybe somehow, and the car could be autonomous, programmed to, okay, so you're drunk, you're not going out today, I'm gonna take you home. You're not going nowhere today, I'm gonna take you home. What do you think of this view? Of course, thinking that we are in a non-autonomous, fully autonomous car scenarios yet.
Well, of course, I haven't spoken about communication between cars, but I think that's a very important thing. It needs to happen. It can make cars aware of cars that you cannot see, even behind a corner, right? And so communication between cars, absolutely a must. Cars giving you a penalty, I'm not sure. And it makes me a little bit wary, to be honest. To have your car now also being your next policeman. I want it to be my best car, not to be my best friend, necessarily.
I was thinking something maybe the cars has a log system somehow, and month by month the traffic regulatory agents could download that information from your car and check if you are being a good driver, or if you are being a bad driver, or if you're going to get your license suspended somehow. I was thinking about this. So do you think this is a bad idea?
Yeah, well, it's of course no wonder that there is this battle between the apples and Googles and so on of this world, and then the car manufacturers, because in the end, this will be a massive source of data. And I hope it will not eat away too much of our privacy, to be honest.
Okay.
I'm not a big fan of police states.
Oh, I see. I'm not either, but I think you remember, I think you know somehow, I'm not going to talk any further about this. I think you know the traffic here is pretty bad. It can get pretty bad in certain regions.
Yeah,
here in
left
Brazil.
and then right and then cross the road.
So I always get angry when I see, oh my God, what's this guy's doing right now? I don't think he's should be driving. I think this guy should be home. What is he doing in the road? So I thought this years ago. I'm not a fan of police repression leaders. So but anyway, I thought this job being done autonomously or behind the scenes by the cars would be a good idea. I don't know.
Yeah,
anyway.
Well, it's a source of data. It will definitely be used, that data, for the better or the worse. Let's see.
Let's see what it gets.
One has to be careful.
Okay, Professor Van Gogh, thank you very much for your talk today. We are very honored to have you here with us. So,
Muito obrigado.
muito obrigado, Professor.
I think you can talk in Portuguese.
No.
Oh.
Infelizmente, no.
Oh, your Portuguese is very good.
No, it isn't.
it's better than my English, actually. So thank you very much, Professor Van Gogh. We're going to resume with the technical sessions for today. I think the next session is control and robotic systems. Professor Eduardo Tots will be the chair of the session.
Morning. All the presenters are already here, and Professor Eduardo is already there, and I think he could start anytime. Also, Professor Eduardo, I'll be playing the videos, so if any of the presenters wants a video playback, they can ask me.
Okay. Is Davi here or Luis will represent?
Let me just thank you, Luke, before you start, Fernando. It was really a pleasure for us to having you here, Luke, and you are invited to watch the sessions and to stay here with us if you would like it. We would like very, very, very much to thank you. Okay.
Thank you very much.
Okay, Eduardo.
Thank you for your presentation also. Well, we will start the session Control and Robotic Systems now. The first paper is Performance Evaluation of Propulsion Control Techniques for Autonomous Sailboat from Davi Santos and Luis Gonçalves.
Yes, I'm here. Can you guys hear me?
Yes.
Nice. So let me open my camera. Can I share my screen now?
Please.
Okay, thank you.
I will shut off my camera now.
So hopefully you're seeing what I'm seeing here. Oh, hi, my name is Davi, and I'm going to present the paper Performance Evaluation of Propulsion Control Techniques for Autonomous Sailboats. So first, a quick motivation. We have in NATONet laboratories of UFRN a robotic platform named N-Boat. And the N-Boat is an autonomous sailboat that is used in support platform for other UAV missions. And the main advantage of a sailboat is that it uses the wind for propulsion. So a sailboat have a large energy autonomy compared to propelled or conventional propelled robots. And one of the important parts of the navigation system for a sailboat is the propulsion control. And the literature presents many propulsion control techniques, but we couldn't find any kind of performance comparison of the performance of the techniques. So the question that we try to answer with this paper is, which propulsion control do we use for the end boat? And the contributions of these works are the comparison framework using ArduPilot, the implementation of multiple propulsion techniques in this framework, the improved extremal seeking, that is a new propulsion control technique that we proposed in this paper, and also the scenarios and the metrics that we chose to use for evaluation. So as the sailboat uses the wind for propulsion, the movement of a sailboat is given in relation to the wind, as shown in this figure. So we have basically three main situations. So we have the tailwind situation. In this case, the wind hits the sailboat from the back, and so the wind basically pushes the sail and gives the sailboat propulsion. We have beam reaching. In this case, the wind hits the sailboat perpendicular with a 90-degree angle. And we also have the upwind situations. And in this case, it is also possible for a sailboat to navigate. So the sail works as like a traditional airplane wing, and it generates an aerodynamic lift, and this lift translates into propulsion for the sailboat. And noticeably, in the sailboat movement, we have a dead zone. This is around the wind direction of about 45 degrees angle, where the sailboat cannot gain any propulsion because the sail can't generate this aerodynamic lift. So it is not possible to navigate in this direction. We also have the looping maneuver. That is when you move the sail wind direction, like from tailwind to upwind. And you also have the bearing away maneuver. That is the opposite, when you move the sailboat away from the wind, from the upwind situation to the tailwind situation. So this is the basic block diagram for a propulsion control of an autonomous sailboat. So you have as input some environmental technique that you're using. So you can have a speed reference or a heeling reference. Heeling is the rolling maneuver or the rolling movement of a sailboat. And the output is the sail angle. And we choose to evaluate 4 propulsion control techniques. So the first one is the fixed sail angle. And in this strategy, you keep the sail at the same angle throughout the movement. And the main advantage is to, yeah, so this strategy works because for a given sail angle, there's a wide range of wind directions where the sailboat can get propulsion. So the advantage is the low energy consumption, because we noticed that the most energy intensive activity for a sailboat is to change the sail angle. And the drawbacks is the low maneuverability because you don't have an active control of the sail angle. So the second strategy is the linear interpolation. And the idea is to mimic the behavior observed on this figure on the right. So you can notice that as you go from the running situation to the close halt situation, the sail starts at a 90 degrees angle in relation to the sailboat. And as you're looping up, the sail is closing, and it is going to the 0 degrees angle in the dead zone. So those equations on the left try to mimic this behavior or represent this behavior mathematically. And the advantages of this strategy is the ease of implementation, as quickly provides an active control of the sail. And the main drawback is the static behavior for different wind speeds. So it doesn't take wind speed into account. And this is the first strategy that tries to do speed control in an autonomous sailboat, and it's called extremal seeking. And it is a kind of a gradient descendant technique. And the idea is that you have a sail angle step called alpha. And for example, you start open the sail. So you open the sail just a little bit. And then in the next time step, you see if the sail speed increased or decreased. In the sail, if the sailboat speed increased, then you're moving the sail at the right direction. So you keep opening the sail. And if the sailboat speed decreased, that means that you're moving the sail at the wrong direction. So you change the directions and you actually start to close the sail. And the idea is that if you follow this behavior, eventually the sailboat speed is going to converge to the maximum speed of the sailboat for that given direction, wind direction. So this is the main advantage of the strategy. And the drawbacks are the slow convergence. So it takes a lot of time to get to this maximum speed. And also that it can have steady state oscillation if you don't choose the sail angle step properly, as it shows in the figure on the right. So to solve those problems, we propose the improved extremal seeking. And the idea is that it has three main improvements. The first one is that we added a base value to actually increase the convergence speed. So the extremal seeking is going to happen around this sail angle, that is a base value. We also made the sail angle step variable, and it is variable according to an speed error. And the speed error is the difference between the desired speed, a reference speed, and the current speed of the sailboat. So you can also have a better large maneuvers. You have a small time step, so you can make more frequent changes to the sail. And when you have a big maneuver, you don't have to change the sail angle so oftenly, so you can have a better energy economy. So this is a scheme that we use to compare the techniques. So on the left, you have the scenario. It consists of 3 points, point P1, P2, and P3. And from point P2 to P3, the sailboat has to make a heading change of 90 degrees angle. And we have two wind situations. In one, the wind is coming from the 135 direction. So the sailboat has to bear away to get to point P3. And on the other, the wind direction is 315 degrees. So the sailboat has to loop up to get to point P2, from point P2 to point P3. And on the right, you have the navigation modules for the experiment. So beyond having a propulsion control, we also have a heading control and a waypoint following to allow a navigation, a basic navigation of a sailboat. So the idea is that we fix the techniques for the heading controller and also for the waypoint following. And we only change from experiment to experiment, we only change the propulsion control techniques so we can better isolate the behavior of the techniques. And the metrics that we choose to evaluate, the first one is energy. So the energy is the accumulation of a sail angle throughout the experiment. Time, it is the time that it takes to get from point P1 to point P3. And also safety, that is the maximum healing in the experiment. The tools that we use, so we chose to use the AutoPilot, and the AutoPilot provides a software in the loop tool. And the first interface is the command line, so you can change the parameters of the robot and also the simulation. The second interface is the telemetry interface, so you can see parameters of the sailboat. And in the third, we have a map of the environment, so you can see the trajectory of the sailboat. And the main advantage of the AutoPilot is that you can also use the same code that you use in the simulation, you also use in the real robot. So for the experiments, in the first experiment, looping up on the right, you can see the trajectory. And despite only changing the propulsion technique from experiment to experiment, you can see that the trajectory is quite different for some of the propulsion techniques. So the blue line is the fixed sail angle, and it deviates quite a lot from the line that is supposed to follow. These are some graphs from the experiment. So on the up left, you have the speed, and the bottom left, you have the sail angle. And In the pink curve, you can see the pink line, you can see the oscillation that I talked about in the extremal seeking. So it keep oscillating around a point. And I don't know if you can notice there, but the improved extremal seeking keeps a much higher speed profile in this experiment. And on the upper right, you have the sail angle accumulation. And for this metric, the extremal seeking has the worst performance because it keeps changing the sail angle. And on the bottom right, you have also the healing profile in this experiment. So for this experiment, the fixed sail angle had the best energy metric performance because it doesn't change the sail angle. And the total time, the linear interpolation had the best performance, but the improved extremal seeking was close. And for the safety, the extremal seeking has the best performance. And for the other experiments, so in this experiment, the trajectories are similar. There are no major differences between the techniques. And also the behavior that we observed is similar to the other experiments. So also in this case, you have the characteristic oscillation of the extremal seeking. And also the extremal seeking had the worst performance in energy. And for this case, the fixed sail angle has the best performance in energy. The improved extremal seeking had the best performance also both in time and the safety performance. So final consideration. So the experiment showed that the improved extremal seeking removed the oscillations and also has a faster convergence time. And we also got a better understanding of the advantages and drawbacks of each propulsion technique. So we conclude that the best strategy is actually to use many techniques for each situation. So if you want to have a better energy economy and you can afford to lose some maneuverability, you can use the fixed sail angle. And if you want to get faster to the point, to a desired point, so you want a better speed profile, you can use the improved extremal seeking. And we also provide this environment used in simulation in a GitHub page. So if other researchers want to also compare their propulsion control techniques, they don't need to implement the other control techniques. And as future works, we are intended to expand the testing scenarios. So you notice that we only tested for 2 scenarios of wind direction, and we didn't change the wind speed. So we can also change the wind speed and can change the waves, add waves to the simulation and change the water current. We can also use other heading control and waypoint following techniques. So you can see how the propulsion control techniques works when they're working together with these heading control techniques. We can add other meaningful metrics. We only use 3 for now, but you can increase the pool of metrics. Can also prove the improved extremal seeking convergence. And ideally, we want to migrate the ROS to the code to ROS because it is a widely used tool in robotics today. So this is it. I'm available to answer any question, and thank you.
Well, thank you for your presentation. I will check if I have a question here. No. By YouTube, no, but I have one. I found it very interesting your presentation and the problem very interesting. If someone knows how to sail, he knows that it's a very interesting problem. I would like to ask you if you have planned for future work to consider disturbance, such as sudden or very quick wind direction change, for example.
So this is actually a good question. The scenarios that we tested, we keep the wind direction and wind speed static. So we didn't change the wind speed and direction. But in reality, the wind speed and direction keeps changing. And this is one of the challenges of an autonomous sailboat, because the wind is unpredictable, or it's hard to try to predict the wind at a given point, the wind speed and direction.
Yeah.
So this
was a challenge for me also.
Yeah, so ideally you have to add this to add robustness to your propulsion control technique.
Okay, good. Okay. If no more questions, thank you for your presentation. Very nice work.
Thank you.
Then I will announce the next paper. It's already here. Douglas Macaret will present from Federal University of Minas Gerais, multi-dynamic perimeter surveillance by an autonomous robot. Please, you can start.
Okay, can you see my screen?
Yes.
Okay. So, hello everyone. I'm Douglas from UFMG Brazil. I'm with the Computer Vision and Robotics Lab. And today I'll be talking about our work entitled Multiple Dynamic Perimeter Surveillance by an Autonomous Robot. So, perimeter surveillance can be described as the task of monitoring the activity of the boundary of a given region. And the use of robots in these tasks aims not to expose humans to the risks that might be contained inside these regions. Because in real world scenarios, we expect to have like some dangerous situations that are characterized by these boundaries around that region. And in real world scenarios, perimeters can behave in different manners. For example, static perimeters are the ones that we consider they have like negligible changes in short periods of time. And when a region is said to have a dynamic behavior, it means that its perimeter can shrink or expand more rapidly, like in forest fires, oil spills, or radiation leaks. And therefore, keeping track of these perimeters, these regions, can be extremely useful to control the spread of damage and to maintain a persistent and correct monitoring of the activity. So in this paper, we consider the use of a single robot in an obstacle-free planar environment with multiple dynamic regions of interest. And the goal is to have the robot circumnavigate the perimeters of such regions of interest and maximize the total area under surveillance. This problem can be divided into two specific tasks. Initially, we must represent the perimeter. We assume in this work that the detection of the perimeter is outside the scope of our work, and a set of input points are initially given. Next, the representation of the perimeter, we have to define a control strategy to maintain the robot navigating over the curve, or actually over the multiple curves. Considering related work on this problem, we can enumerate different types of works in the literature, and most of them, they have considered the use of one or multiple robots. However, most of them focus on the scenario where there is only one perimeter to be monitored in the environment. Furthermore, generally, the perimeters, they are represented by implicit functions or analytical curves, which restricts its use through more well-behaved dynamic perimeters. And in the case of dynamic perimeters, generally their behavior is known a priori. So we are kind of focusing on these gaps of the literature. So it is important to notice that it's a real big challenge, this entire problem, and that the scope of our problem being tackled in this work was simplified to make it more tractable. And the following assumptions regarding the agent and the environment were considered. In this work, we propose a framework in which our perimeters, they are represented by B-splines, and our trajectory tracking control design is based on a tangent linearization along the reference trajectory. So consider the perimeter representation. The interpolation method select to create paths that will represent the regions of interest is based on the use of B-splines. B-splines provide smooth and well-fit curves, and the computational cost to create them does not compromise the overall performance, reminding that we are considering multiple and dynamic regions along the environment. In this work, we divided the knots of the B-spline into two groups. Samples that belong to the initial set of the perimeter that were given as an input, they're the blue samples here, and also calculated samples, the red ones, which are not part of the original set, and we calculate and introduce them into the problem, so they're used to facilitate the vehicle and navigation and make the navigation more smoother. Considering the dynamic behavior of the regions, it is also important to notice that it might happen for a region to merge with other regions when they intersect over time, or even split into multiple regions when the content that defines a region can be enclosed or it's better enclosed by two or more different regions over time. So it is necessary to define how to represent these different types of behaviors. Considering the merge, when an intersection occurs, first we identify and remove all samples that are internal the intersection of the regions. And for that, we use a modified version of the convex hull algorithm and the alpha shape technique, since the combined region is a non-convex region. So by only using the convex hull is not the best solution here. And then, but after we remove the internal samples, we use all the remaining samples to create a new set of samples representing the unified perimeter and apply a new interpolation. And if necessary, we're gonna introduce new calculated samples there. There are some open spots there, as you can see. To tackle with a split situation, we verify the distance between the samples, and we consider that if this distance between the samples is large enough, so there is enough space for the robot to pass between them, we are going to split this region. In this case, the original perimeter is divided into two, and to avoid like degenerate cases, we consider if the new perimeters will be actually representative enough before doing the split. So if there is just a single sample that's far from the region, we are not going to split it in two. And finally, some calculated samples are also introduced after the split into the knot vector to prevent multiple consecutive splits. And finally, tangent linearization along the reference trajectory will be used for the robot to navigate over the B-spline. This is a simple way to design controllers for trajectory tracking, and it basically consists of the use of a proportional controller and a feed-forward controller. So as mentioned before, here we consider a unicycle model robot, and to proceed with a nonlinear controller design, it is necessary to redefine the state tracking arrow to the difference between the current position of the vehicle and the reference trajectory, as shown in equation 1. Next, with the usage of a nonlinear transformation in equation 2, and we end up with a new dynamic that can be described as equation 3. And finally, a nonlinear design for the trajectory tracking can be defined as shown in the last equation. The stability analysis of this controller is discussed on the paper. Now that we're able to track a single perimeter, it means that we are able to have the robot circumnavigate the perimeter. We must decide the order in which the perimeters will be tracked in the environment. To that, we propose the use of a coverage efficiency metric, which is calculated by the perimeter length over the coverage time. The coverage time encompasses the actual time to completely traverse the perimeter and the traveling time of the robot, where the traveling time is the time necessary for the robot to navigate in a straight line from its current position to the entrance point of the region. And the entrance point is just the closest sample in the perimeter. And finally, we determine the sequence of visit considering this metric and in a greedy manner. We have evaluated our methodology in different simulated environments, and we consider different scenarios. The robot has the following speed constraints, and this table summarizes the integral square errors considering the tracking in X and Y for all the experiments. On these videos, we can see the execution of the methodology. On the first experiment, experiment 1, we consider just a simple case of a single perimeter in the environment which changes over time. And we can see that the robot, the vehicle, is able to correctly track these changes over time. On experiment 2, we show a scenario where multiple perimeters they end up merging into a very complex form. And again, the vehicle is capable to continuously track this perimeter. And finally, on experiment 3, it's the case where perimeter, an initial single perimeter, it splits into 2 other perimeters, giving the behavior of the samples over time. And the vehicle, it has to keep tracking both of the new boundaries of the regions. These figures show the tracking errors in X and Y for all scenarios. And as can be seen, the vehicle is capable of tracking the perimeters in all cases, as the tracking error tends to 0. Finally, in this paper, we have proposed the use of B-splines for the perimeter representation, which allows to consider more generic shapes than, for example, analytical curves. We also presented a navigation strategy based on tangent linearization for trajectory tracking, when trajectories are represented by B-splines. Another contribution relies on the fact that by limiting the values of the actuators on the system, we provided a technique more suitable to be actually used in real robots that have a differential model. And as future work, we intend to evaluate other types of controllers and consider multi-robot systems. And finally, we expect to apply the methodology in a real-world surveillance scenario. Thank you, and I'd be happy to answer any questions.
Thank you very much for your presentation. I will check if I have a question here. No, and also no. I would like to ask you or to invite you to make a consideration about using the split procedure and maybe the merge also in order to manage the autonomy question of the robots. For example, if you have an UAV that has limited autonomy, maybe you could choose to split and merge regions in order to keep in mind to be compatible with the autonomy of the vehicle.
Yes, that's a good question. And in the paper, we mentioned that a possible other future work is actually to consider this idea of routing. So instead of greedily selecting the perimeter to visit, giving this coverage efficiency, actually we can introduce other aspects. For example, the energy of the vehicle, different kinds of vehicles, for example, heterogeneous teams. So that's actually also a future work we intend to tackle, and we think it's really important. And also considering the merge and the split, these are also simple initial ideas to make the merge and to make the split. And actually, the split is the more problematic case. So it is also important to think on a more on a better representation for this case on the split, considering different types of other characteristics of the vehicle.
Okay, thank you very much, Douglas, for your presentation. Now I will invite the next presenter, José Nuno, from the University of São Paulo, to present his paper, Gain Schedule Robust Recursive Lateral Control for Autonomous Ground Vehicles Subject to Holotopic Uncertainty.
Good morning, everyone. Can you guys hear me and see me as well?
Yes. Yes.
Okay, great. I will share my screen.
Please go on.
Okay. Can you see the presentation?
Yes.
Let's see, it's working. Okay. So hello, everyone. My name is José Nuno. I will present you the work named Gain Scheduled Robust Recursive Lateral Control for Autonomous Ground Vehicles Subject to Polytopic Uncertainties. The authors of this work are with the São Carlos School of Engineering at University of São Paulo in São Carlos. Let's start. So the presentation is organized as follows. First, I'll give you a brief introduction about the subject investigated throughout the paper, and then we'll define the lateral dynamics model for our ground vehicle. And then I will present you the control techniques applied to solve the lateral control problem when the system is subject to polytopic uncertainties. And then we'll check the numerical results obtained with the simulations in MATLAB. And finally, we will draw some conclusions to finish the presentation. As we all know, lateral control is critical when we deal with operation with autonomous vehicles, autonomous ground vehicles more specifically. And uncertainties might degrade the system or even unstabilize the system, which means that the uncertainties might drive the eigenvalues to unstable regions, okay? And as a consequence, many accidents can happen involving the vehicle itself, passengers, pedestrians, and surrounding vehicles. So it's important to take these uncertainties into account while performing vehicle control. In this scenario, in the past few years, gain scheduling control had presented a few promising solutions, as we can see in these examples of references. Therefore, the objective of this work is to solve the lateral control problem for an autonomous ground vehicle when the system is subject to polytopic uncertainties. And to achieve this goal, we will combine the robust recursive regulator presented by Tea, Seri, and Ishihara with gain scheduling control techniques. Okay. Now let us define the lateral dynamics model for our ground vehicle. The model is defined based on the tracking errors with respect to a reference path or trajectory. So we have as our state vector x, the lateral velocity, yaw rate, lateral position, and orientation errors as given in x of t. Then we can define a linear parameter varying model in terms of these tracking errors as given in equation 2. In equation 1, I'm sorry, there was a window covering the number. And the matrices, state matrix A, input matrices B, as well as their elements are depicted below. Okay. We see that the coronary stiffness coefficients CF, CR, and the inertial moment IZ, they vary with time. Okay. Now let us discretize the model to obtain a more general form for a discrete time system as in equation 2. As I said in the previous slide, we assume that the coronary stiffness and inertial moments vary within the intervals given in equation 3. Therefore, we see that matrices Fi and Gi become functions of CF, CR, and IZ. Now, by introducing the pair Di composed by these matrices Fi and Gi from the discrete time model and given that the pair belongs to the polytope defined in equation 4, we can combine the extreme values of CF, CR, and IZ and define 8 vertices as given in equation 5. And therefore, we must compute a feedback gain to each of these systems, of these subsystems, and then use a switching control strategy to define which of these gains shall be used at each iteration. Let us now go through these techniques. To compute the feedback gains for each of the subsystems, we will apply the robust recursive linear quadratic regulator. The method was designed for a discrete time system of the form of equation 6, when the uncertainties delta F and delta G are modeled as in 7. To compute the feedback gain, we must first solve the min-max optimization problem given in equation 8 with cost function j sub I of mi given in equation 9. Here, in the cost function, we have matrices P sub I plus 1, K sub I, and R sub I positive definite, and they are weighting matrices in this cost function. And the parameter mi is a penalty parameter related to penalty functions method. So the solution of the min-max problem yields the robust recursive regulator as given in equations 10 and 11. In these equations, matrices L represents the closed loop system, matrix K is our feedback gain, state feedback gain, and matrix P is related to the solution of a Riccati equation. Okay. But before applying the method described so far, we must perform these following identifications in order to fit our lateral dynamics model into the framework derived for the RLQR algorithm. So we are now able to compute the feedback gain for each of the subsystems we obtain from the combinations of CF, CR, and IZ. Therefore, we must determine a switching strategy to choose at each iteration which of these 8 gains shall be applied on the system to close the loop. Okay. In other words, we must determine a parameter Xi in order to have a feedback gain K of Xi that stabilizes the system even in the presence of polytopic uncertainties. Recall that from equations 10 and 11, we are able to obtain a feedback gain K and a positive definite matrix P for each of the subsystems. Therefore, according to Jeromel and Colonelli, if we adopt the switching strategy given in equation 13 to determine the parameter Xi, we are able to stabilize the closed loop system with the feedback in K of Xi belonging to the set calligraphic Ki. Also, remember that the set calligraphic Ki is composed by the 8 feedback gains computed with the robust recursive regulator algorithm. Now let us go through the numerical results of simulations. For our simulations, we chose the task of performing a double lane change maneuver with the vehicle. And we selected such task because it resembles realistic situations such as vehicle overtaking and obstacle avoidance. To define the vertices of our polytope, we use the given intervals for CF, CR, and IZ and combine these extreme values to obtain the pairs DI to D8. Also, we use these sets of parameters to define the RLQR algorithm and consider a non-zero initial error as given initial condition x0. In this work, we performed a total of 1,000 Monte Carlo experiments, and the results are average. With equations 10 and 11, we were able to compute these 8 feedback gains, and with the gain switching strategy given in equation 13 to determine the parameter Xi, we're able to select one of these gains at each iteration, okay? And with these gains and the switching strategy, we are able to obtain the following numerical results. In figure 4, we see the lateral position and lateral velocity errors. Note that in the first few seconds, the error already converges to 0 and the vehicle tracks the reference trajectory defined for these two variables. Now in figure 5, we see orientation and yaw rate errors. Also within the first 5 seconds, these errors already go to 0 and the vehicle successfully tracks the reference trajectory. In other words, it successfully performs the double lane change maneuver. Here in figure 6, we see the reference steering angle to perform this maneuver, along with the steering action provided by the gain schedule robust recursive linear quadratic regulator. Note that this peak at the beginning is related to the initial control action required to bring the vehicle back to the reference trajectory, since we assumed non-zero initial error. Okay? And after a few seconds, the control action provided by the gain schedule RLQR correctly tracks the reference steering angle. Here in figure 7, we see the resulting motion for our ground vehicle with the gain schedule robust recursive regulator. And the vehicle, as we can see, performs the double lane change maneuver correctly tracking the reference trajectory with the steering actions provided by the proposed method. For comparison purposes, finally, we applied the standard linear quadratic regulator defined by the same set of parameters as the ones used in the recursive regulator to control the vehicle. In figure 8, we see that at all experiments, we have at least one unstable eigenvalue, and therefore the standard linear quadratic regulator was not able to deal with the uncertainties. In other words, if we use a standard linear quadratic regulator to control our vehicle, the vehicle will drift away from the reference trajectory. So, in this work, we investigated the lateral control problem for autonomous ground vehicles when the system is subject to polytopic uncertainties. To define the vertices of our polytopes, we consider different road and load conditions represented by the cornering stiffness coefficients and yaw moments of inertia. To tackle this problem, we presented a gain-scheduled robust recursive linear quadratic regulator, which combines a robust feedback gain computed for each subsystem, and then we use a gain scheduling strategy to define at each instant which of these gains shall be used to close the loop and control the vehicle. As we saw in the numerical results, the proposed method is able to stabilize the system even with the polytopic uncertainties, and the vehicle successfully performed the double lane change maneuver. Finally, our work emphasized the relevance of taking uncertainties into account while performing vehicle control. In fact, using robust controllers, we provide greater safety for surrounding vehicles, passengers, pedestrians, and the vehicle itself. Now I finish my presentation and thank you all for your time and your attention.
Thank you very much for your presentation, José Nuno.
Thank you. Stop sharing.
You check if someone has a question here. Not yet. Okay. Well, you have very good results. I was just wondering about the convergence. You have a very short overshoot in the beginning. If you are working with high-speed vehicle, probably you should have a shorter reaction time, I suppose. Which speed do you think that works well your control strategy. And the switching of the gain was very great according to the conditions. I like it. It was
yes. Our work is intended to control urban vehicles. So we assume that the velocities, the longitudinal velocities, they are constant and they are not so high. So the control actions, even if they are not incredibly fast, they are able to perform the lateral control. About the switching, it was interesting because many papers dealing with gain scheduling control, they use LMIs to define the control gains as well as the gain scheduling strategy. And as we saw, the regulator is recursive. So we escape from the LMIs, and maybe this is what causes the convergence and the nice behavior of the gain switching.
Yeah. Thank you. Well, I don't see any question. Well, thank you for the presentation. I will call the next presenter then. We have the next presenter, Igor Lopes from Federal University of Rio Grande do Norte. Left inverse non-linear controller to RRR manipulator.
Hi, can you listen and see me?
Yes.
Okay, I'll share my screen now. Can you see the screen?
Yes, go on, please.
Okay, my name is Igor. I am from UFRN, and the authors of this paper are Samar Dias, Kuros Queiroz, and I. It's about a left inverse nonlinear controller to a RRR manipulator. Here I'll talk about the motivations of this project, the methodology used, show some results, make some discussions about them, make some final considerations, and show the future perspectives. The first motivations of this project are the results obtained by Diaz in his paper from 2016. There he uses an adaptive controller associated with a left inverse system to control a 2-degree of freedom manipulator robot. Here we'll check the left inverse system associated with a PD controller in a more complex dynamics, a 3-degree of freedom robot manipulator. Then we compare the performance of the PD controller with a simpler controller, a servo motor, and we show the simplicity of the controller implementations after the initial calculations. Here on the right, we have a figure of a diagram of the robot. We considered 3 rotary joints and 3 cylindrical links. And the first thing to do is to calculate a cinematic model. For that, we used the Navitt-Hartenberg parameters, putting some systems of coordinates from the base to the robot manipulator tools. In this table, we have the parameters calculated for this manipulator. And after the Navitt-Hartenberg parameters, we can calculate the rotation matrices and the positions vectors of each system of coordinate from the parameters. Then it is possible to calculate the angular velocities, the linear and angular accelerations, and the accelerations of the center of mass, all of them from the base until the arm 2. In here, for the center of mass acceleration, we use the notation PG, that is the position of the center of mass. In here, we consider that the center of mass of each link is in the center. And after the calculation of the cinematic model, we can calculate the dynamic model, calculating the efforts on the joints, the torque N and the force F from the arm 2 to the base. And as all the joints are rotary ones, we consider the torque around the z-axis. So here the effort considered is the torque around the z-axis. And for the calculation of the torque, it is necessary to calculate the inertia tensor of the links. As I said, we consider cylindrical links, and the result is this matrix here. On the right, we have a table showing the parameters of the manipulator to calculate the models. We have the mass, the radius, and the length of each link. And finally, after the calculation of the torques, we rearrange the vectors and matrices to the Newton-Euler model, where we explicitate the inertial reactions, the Coriolis and centrifugal reactions, the damping reactions, that in this case we consider null, and the gravitational reactions. Sorry. After the dynamic model of the manipulator, we calculate the dynamic model of the DC motor. That is the actuator of the joints. For that, we use the Kirchhoff voltage law and the electrical diagram here on the left. The equation results voltage source, and we will use that motor torque. In this table, we have the motor parameters considering an armature inductance null. So considering that the back EMF voltage is proportional to the angular velocity of the rotor and the motor torque is proportional to the armature current, these two equations here, we can apply these to the Kirchhoff voltage law and isolate the motor torque, resulting in this equation. So here we have the torque applied into the manipulator with a voltage source and measuring the angular velocity of the motor. But in this case, we are using a reduction gearbox with a gain of 96 between the DC motor and the manipulator's link. So the relation in between the manipulator torque and the motor torque is given by this equation here. And substituting the values from the previous equation, considering that the link's angular velocity is 1 over kgb, the motor velocity, will result in these equations. In a vectorial form, considering that every line of the vector is one of the motors, we will have this equation here. Considering now the left inverse system, Diaz proposed this equation for the left inverse system, but here we have to consider the dynamics of the DC motor. Then we will modify it to a torque control coming from the left inverse system and going to an inverse system of the motor that has a voltage output and receives the torque signal coming from this manipulator inverse system and the angular velocity also from the inverse system. The main difference from the computed torque abordage here is that we doesn't need the measure of the manipulator's angular velocities and angular accelerations. Here we use the inverse system returns. And then applying these to the manipulator and to the motor, we'll have a plant of a double integrator with a reference signal as an input and the angle of the joint as an output. Here we have a block diagram of the system that has the control signal here coming into the left inverse systems that generates a torque signal to the inverse motor. The inverse motor generates a voltage source that goes to the actual motor that generates a torque to the manipulator, and then we measure the angle joints. The controllers used in this project firstly was a PD controller following this law of control. And we used the Ziegler-Nichols closed loop method to tune the plant result, the double integrator plant. Then for the a fine-tuned tuning was made by trial and error to adapt to the parameters requisites. For the servo motor control, we used a nominal plant. That's because we consider that the motor was detached from the manipulator, a servo motor. So the control law was made detached, and then we tried it attaching with the manipulator. Here we consider the inertial momentum and the damping coefficient of the motor, and then applied the PID control law using the Ziegler-Nichols closed loop method. Then we made also a fine tuning by trial and error to compensate the error that in the project. So the results are, the project requirements were the stabilization time less than 1.5 seconds and no overshoot in the output signal. These are the results for the PD controller in the Ziegler-Nichols closed loop method, and then with the fine tuning. And these are the ones for the servo motor. The simulation specifications were 10 seconds durations, Euler method for solving ODEs, and an integration step of 0.001 seconds. We simulated two scenarios. The first one was moving only one joint at a time to test the decoupling of the inverse system. In the second one, we moved all the joints at a time to test the robustness of the system. Following to the results here for the PD, in the aerodynamics, we see that we have stabilization time less than 1.5 seconds, and all the errors tend to 0. And we have also decoupled movement between the joints. As for the servo motor, we have oscillations and many overshoots in the signals and coupled movement. Here we should only move the first joint, but all the other ones are moving too. And a regime error associated with the second joint here. That is because of the gravity that the servo motor cannot compensate. For the second scenario, we maintained a good performance by the PD controller and an aggravated performance by the servo motor. Here we have more oscillations and a higher regime error in the second joints. So here we can conclude that the presented decoupled technique combined with the PD controller presented the desired performance, while the PID servo motors were unable to meet the criteria proposed. Also, the technique used to decouple the systems allows the use of a simpler controller, maintaining the good performance. Here we use a PD controller to control a nonlinear system. And the future perspectives are to implement this proposed technique in a real RRR manipulator and to design an adaptive controller to also apply it to the left inverse system to make it more robust to parametric uncertainties. And then I finish my presentation.
Well done. Thank you for the presentation.
Thank you.
You'll check about the questions here. No questions. Well, you achieved a good performance, considering that you have PID controllers, no?
Yeah.
It was interesting to check that you done it with Ziegler-Nichols. I worked with that about 20 years ago in industry.
Yes.
PID for machines. And
it was to prove that we can simply control the system with the inverse system, with the left inverse systems.
Yes, and you were not able to meet the criteria, but do it to the motors, not to the control, as I understood. Could you talk a little about that?
Here in the servo motors, you say?
Yeah. Mm-hmm.
Yes, because we can control the servo motors rotors. Okay. We made the tuning detached from the manipulators. There, the PID control did meet the criteria. But when we attach them in the manipulators link, links, then it wasn't able to meet the criteria. Here we can see that many oscillations were mainly because it's not considering the dynamics of the manipulator's links.
Probably because then you have a completely different dynamics. No? Okay.
Yes.
Okay, thank you very much for your presentation.
Thank you.
You call the next presenter. Next presenter is Fabian Andres Lara Modena from Federal University of Technology, Paraná. Kinematic analysis of planar 5R symmetrical parallel manipulator using an interval approach. Okay, you have a video presentation. Let me start.
Okay.
Okay, go on.
Hi, my name is Fabian Andres Lara Molina, and I'm going to present the work entitled Kinematic Analysis of Planar 5R Symmetrical Parallel Manipulator using an Interval Approach. This work was done in cooperation with Professor Edson Hideki Kolovishi. The parallel manipulators are subject to clearances or positioning errors that deteriorate the overall performance of the mechanism. These errors are introduced by manufacturing, assembly tolerance, variations in the geometrical parameters, and also positioning errors of the active joints or actuators. Therefore, it's necessary to quantify the effect of this error in the kinematic performance of the manipulator. Therefore, it is necessary to develop new numerical methods to quantify these errors. The probabilistic approach has been widely applied to analyze the effect of errors in the manipulator. Moreover, as an alternative, the Brody approach was used also, and also interval analysis has been used to analyze the effect of these uncertainties. The present contributions consider the error as intervals. Therefore, the proposed approach to evaluate the interval uncertainties has three main stages. First, the kinematic model was formulated by including the interval errors. Then, an interval approach based on the kinematic model was formulated to compute the position of the n effector by taking into account the uncertain interval error. And finally, we analyze the results by comparing the results of the proposed interval approach with the Monte Carlo simulation method. This is the outline of my presentation. First, initially we have the parallel mechanism. Basically, we have two kinematic chains, two active joints, and the n effector is located at the point P. The position is defined by two Cartesian coordinates, x and y. In the active joint, we introduce the positioning error defined by delta theta 1 and delta theta 2, and these errors are defined as intervals. Then we consider the inverse kinematics based on the kinematic constraints of the manipulator, defined by these two equations. By solving these kinematic constraints, we obtain the delta E, which is the angle of the active joint, defined as a function of the positioning error of the n effector by using the expression of this equation. Then the forward kinematic model also considers the kinematic constraints. And the objective is to determine the position of the n effector as a function of the active joints. By solving these equations, we obtain the expression to evaluate the position of the x coordinate and the y coordinate of the n effector by solving this quadratic equation as presented in this expression. This is the solution for the y coordinate. And then we define the workspace of the manipulator by defining the bounds for the inner and outer bound of the that is imposed by the first kinematic chain and the second kinematic chain. In this example, we consider the usable workspace that is bound by the internal and external limits of the chains, and also the limits imposed by the singular lossy positions in the blue line, as presented in this figure. Okay, regarding to the interval approach, we consider the forward kinematic model that is represented by M. P is the position of the n effector, F is the forward kinematic model, theta is the definition of the active joints, and delta theta is the positioning error. In this approach, we introduce the interval uncertainties in the positioning error delta. Therefore, we have delta theta bar, and therefore we will obtain an interval positioning for the n effector of the manipulator. Therefore, we have to evaluate this interval output, this interval position of the n effector. And this evaluation is obtained by solving the optimization problem shown in this equation. In this optimization problem, we will obtain the maximum and the minimum limits for the x and the y coordinate. Therefore, we have for optimization in order to estimate the interval response, or better, the interval outputs for the x and the y coordinate of the n effector of the manipulator. In this figure, we observe the geometrical interpretation of the response. Basically, in the planar Cartesian workspace, the interval approach is associated to this rectangular. The interval response of the manipulator is a rectangular. Within the rectangular, we observe the estimation of the error by using the Monte Carlo method. And initially, we can see that the interval approach overestimates the error by comparing with the Monte Carlo simulation method. Therefore, it's necessary to improve the interval approach. And in red is the improved interval approach that I'm going to present now. This improved interval approach is obtained by including additional points to analyze the interval solution, and we introduce two additional points, and the optimization problem is presented in this equation, and we observe that this optimization problem considers additional constraint that is function of the inverse kinematic problem. Therefore, with these additional constraints and these additional analyzed points, we can fit the interval solution with the Monte Carlo response as presented in this figure. The numerical results, we analyzed we consider this interval positioning error in the active joints. We also consider different definition of the mechanisms, and we compare the interval approach solution with the Monte Carlo simulation method. The optimization problems of the interval approach were solved by using the generic algorithm method. Initially, we consider this definition for the mechanism with these linked lengths, and we analyze the interval response at this specific position of the end effector. We obtain initially the interval response defined by this rectangular. Then we obtain the improved interval solution. Then we estimate the uncertain response with the Monte Carlo method. And finally, we analyze the three methods in this figure. We can see that the improved interval approach has a better performance than the initial uncertain interval approach. Then we analyze three cases for three different definitions of the mechanisms. Initially, we have the case A. Now we analyze 6 different positions within the workspace. For these 4 solutions, we observe the same behavior that in the initial case. The improved interval approach has a better performance than the initial interval approach. Then in the case B, we also consider 6 cases. We can see that the interval approach, the initial interval approach, overestimates a certain response. Nevertheless, this solution is improved by the improved interval approach. And then we have the case C. Also, we analyze 6 different positions and we obtain an interval solution for these 4 positions, and the results are quite similar to the previous case. As a conclusion, the kinematic of the planar manipulator was analyzed by considering the uncertain interval active joint error. The kinematic model was considering by the forward, the inverse, and the workspace model. The positioning error was modeled as interval, and the kinematic performance permit to describe the n effector interval errors of the active joint and the positioning errors of the n effector of the parallel manipulator. Future work will analyze the dynamic behavior of the mechanism by consider the dynamics with uncertainties. The acknowledgements for the sponsors, and thank you for your attention.
Well, thank you for the presentation. Let me check if you have questions here. Not also. Well, it's very dense analysis. It's not so easy to follow your work, but it's very interesting. I would like to ask you, what do you think is the strongest point of your approach? Because you are using an interval approach for a parallel manipulator. What do you think is the strongest point that make it the algorithm of choice to control?
Well, I think that the most the stronger point of my work is to analyze the uncertainties as intervals. When we analyze these uncertainties as intervals, we can consider a simpler model of the uncertainties that do not have into account the density of the probability of the when comparing with the with the random uncertainties. And I think that is a good point. And I think that another strong point is that this analysis is a previous analysis that will permit to evaluate the kinematic behavior and also the dynamic behavior of the manipulators. For example, in a control approach, we can analyze how the uncertain inputs, for example, the uncertain parameters or the uncertain disturbances affect the manipulators in a control in an advanced control system approach, for example. And I think that is very interesting to develop these numerical procedures, for example, to evaluate the control system, for example.
Yeah. Okay. Thank you. Well,
thank you so much.
Thank you for your presentation. We finished then this session. Thank you for all for coming, for staying with us, and please come back in the afternoon. Okay, thank you. Bye.
Thanks, Professor Eduardo. I think Professor Luis will just close the session for today, and we are going to go, we are back after lunch break.
Yes, okay, thank you.
Luis?
Yeah, that's it, Julio. Thank you so much, Eduardo, for the morning section. And we will be back in the afternoon at 2 p.m. Sorry.
Yeah, 2 p.m.
Okay.
Thank you very much, everyone.
Thank you also. Bye.